Okay, so we start today's lecture. In the last lecture, we introduced a network, voltage, and a flow, and effective resistance. So voltage is just a harmonic function on the network, and there is a source, there is a sink. So except the source and the sink, it is harmonic at other vertex. The corresponding current flow is the difference of the voltage divided by the resistance. And the effective resistance is the voltage. The effective resistance is the difference of the voltage at the source and the sink, normalized by the strength of the current flow. So in this definition, we already explained in the last lecture that this way to define effective resistance is independent of the choice of the voltage. So if you change to another voltage, it will give the same effective resistance. So the effective resistance is a quantity defined for the network. So it has nothing to do with the voltage you choose for the network. And today, first, we will introduce another notion about the network. It's called energy of flows. And then we show the relation between effective resistance and energy. And then introduce Nash-Williams inequality. So this is the first part of today's lecture. And the second part, we will discuss countable state space Markov chain. And there is the most important difference from the finite state space chain is there is two different notions, recurrence and transience. So there's no such notions for the finite state space. But for countable state space, the first difference is there are two scenarios. One is called resistance and transience, and another is called recurrence. Okay, so we start with energy of a flow. So suppose theta is a flow on the network from A to Z, from the source to the sink. The energy of this flow is defined in this way. In this summation here, note that this summation is over n-oriented edges. So just a notion here. So for a flow, when we define the flow is defined on oriented edges, and it is anti-symmetric. But when we define the energy of flow, because we have a square here, so the direction of the edge doesn't matter in this expression. So here we are just summing over all n-oriented edges. Okay, so this is the definition of energy of flow. And then the first theorem says the relation between effective resistance and energy of flow. So the relation between effective resistance and energy of flow is, it is the inf of energy of the energy of all the unit flows. So before we prove this theorem, we can say that on the one side, this theorem tells us the relation between effective resistance and energy of flow. On another side, if we want to find the upper bound for the effective resistance, it is sufficient just to find some unit flow. And for any unit flow, the energy of this flow will give an upper bound on the effective resistance. Okay, so why this is true? The proof has 3 steps. First, for any unit flow, we know that for this flow on every edge, the flow on each edge is a real number between 0 and 1, because this is a unit. So the total current the total flow in the network is 1. And so for each edge E, we know that theta E is just a number between 0 and 1. So this implies that this energy of a flow is just a function on a compact subset So the energy of flow is just a function on the compact subset of this region, and it's still compact. So since it is a continuous function on the compact subset, we know that the minimum is always obtained. And for any flow that attains the inf, we say it is a minimizer. So, but at this step, we don't know whether there are several minimizers or just one minimizer. The only thing we know is the inf can be obtained at some point. And at all the points that it attains the inf, we say it is a minimizer. Okay, so this is the first step. Second, we will show that any minimizer has to be the current flow. So after the second step, we can see that the minimizer is unique because any minimizer has to be the current flow. And the third step, we will show that for the current flow I, the energy of the current flow is exactly the effective resistance. So this is the three steps of the proof. So after we prove the third step, we complete the proof of the theorem. Okay, so we continue the proof with second step. Any minimizer has to be the current flow. Suppose that theta is a minimizer. In order to show it is a current flow, it is sufficient to show that it satisfies the cycle law. So recall what we proved in the last lecture is any flow that satisfies cycle law has to be the current flow. So this is what we proved in the last lecture. In the last lecture, we showed that the current flow satisfies the cycle law, and the cycle law also characterizes the current flow. So for any flow, if it satisfies the cycle law, then it has to be the current flow. So now we want to show that the minimizer theta is the current flow. It is sufficient to show theta satisfies cycle law. Okay, so for any cycle, so this is a sequence of oriented edges and it forms a cycle. And now we define a flow in the following way. So along this cycle, in the right orientation, the flow equals 1. And in the reverse orientation of the edge, it is -1 because we need, this is a flow. It is a flow, it has to be antisymmetric. So in this way, we can say that gamma is a unit flow. And moreover, we can see that theta plus epsilon gamma is a unit flow. For any real number r, for any real number epsilon. So theta itself, it is a unit flow, and now we just add a cycle on top of this unit flow, and it's still a unit flow. Okay, since it is a unit flow and we assume that theta is the minimizer, so what we must have is for any epsilon, the energy of this theta plus epsilon gamma has to be greater than the energy of theta, because theta is a minimizer. And then let us check what's the difference between these two energies. Okay, and for this summation, we know that only when E is on this cycle, this gamma is not 0. Otherwise, it is 0 all the way. So of course, the first summation will cancel with this with the second summation if E is not in this cycle. So the only remaining thing is when E is in this cycle. Okay, so now we expand this square. Okay, so this is the difference between these two energies. And we know that it has to be positive for any epsilon. So first, suppose that this epsilon is positive and very small. We divide both sides by 1 epsilon. Then we have this summation plus an O epsilon term that is always positive. And then we let epsilon goes to 0. This will tell us this summation has to be positive. So let epsilon be positive and approaching 0. We know that this quantity is always positive. And then we let epsilon be negative and approaching 0. This would imply that this summation is always negative. And combining these two, we see that this quantity has to be 0, and this implies that theta satisfies the cycle law. And since it satisfies cycle law, we know that it has to be the current flow. So for any minimizer, the minimizer has to be the current flow. So there is a unique minimizer. So this is the second step. Okay, for third step, we need to calculate explicitly what is the energy of the current flow. So now suppose I is the current flow. Unit current flow. So what is the energy of this unit current flow? So in this expression, we are summing over all n-oriented edges. And now I just want to write each edge by its two endpoints. So from here to here, I just write out all the edges by its two endpoints. And because in the second summation, we sum over all possible x and y. So in fact, for each edge, we counted it twice. So we need to normalize it by 1/2. Okay, so for the current flow, we know that I is the difference between, I times the resistance is the difference between voltage. This is Ohm's law. So I times the resistance equals the difference of voltage. Okay, so now we write this two parts separately as two summation. And here we can see that in the first summation and in the second summation, the only difference is we just switch the role of x and y. And since we know that this current flow is antisymmetric, so if we switch the role of x, y in the second term, then we will have a plus sign in front. So this tells us, in fact, these two parts of the summation are exactly the same. Okay, so now let us check what is this summation. So now we are summing over all possible x and y. And the function here is, this only depends on x. And here depends on y. So if we first summing over y, we're just summing over here. And for the current flow, we know that if we're summing over all possible y for fixed x, then this is exactly the divergence of I at vertex x. And since this is a flow, we know that the divergence is almost zero everywhere, only except at the source and the sink. And at the source, we know that the divergence is +1. And at the sink, the divergence is -1. And at all other vertex, the divergence is 0. And this is exactly the same definition for the effective resistance. Okay, so this theorem tells us the relation between effective resistance and energy of flows. So this theorem has many useful applications. So first, for example, if we have the same network, but the network has two different sets of resistance, then from this theorem we can see that if the resistance is increasing, then the effective resistance is increasing. Okay, so if we have a fixed graph, but if we have two sets of resistance on the edges, R and R prime, so these are two different sets of resistance on the edges, and if we have that R is always less than R prime for every edge, then we can see that from the relation between effective resistance and energy of flow, it is immediate that the effective resistance calculated with respect to R has to be less than the effective resistance calculated with respect to R prime. Okay, so first a quick proof of this guy. So suppose I prime is the current flow, the unit current flow with respect to the resistance R prime. Then we know that I prime is also a unit flow with respect to R. So by the theorem that tells us the effective resistance and energy of flow, we know that this effective resistance is always less than the energy of I prime because it's just one unit flow and it is not the current flow with respect to R. But it is the current flow with respect to R prime, so this is exactly the effective resistance when we calculate with respect to R prime. Okay, so this is the first application of the theorem, the relation between effective resistance and energy of flow. And from here, we can see that if we add one edge to the network, so we can imagine before we're adding this edge, this resistance between these two vertices is infinity because there's no edge. And after we add this edge, the resistance becomes something finite, so we decrease the resistance. And this implies that the effective resistance will also decrease. And because we know the effective resistance, there is a relation between effective resistance and escape probability. So this tells us if we add one edge to the network, then escape probability increase. So this is not immediate at the first sight. So if I just tell you that I want to add one edge to the network, and I ask whether the escape probability increase or decrease, so there's no direct calculation showing that it is increase or decrease. But by the relation between effective resistance and energy of flow, we can immediately see that we add an edge, then the effective resistance, the escape probability will increase. And also, if we glue two vertices in the network, so this means that before we glue it, the resistance between these two vertices is something finite. And after we glue it, the resistance becomes zero. So we are decreasing the resistance. And then effective resistance also decrease, and escape probability increase. So this is the relation between effective resistance and escape probability, effective resistance and energy of flow. And we can see that there are a lot of interesting applications between all these relations. Okay, so this is the first application. The second application is called Nash-Williams inequality. So we can use the relation between effective resistance and energy of flow to give the lower bound. So directly from the theorem, we know that the effective resistance is less than the energy of any unit flow. So directly from the theorem, we only see that we can find the upper bound for effective resistance. But Nash-Williams inequality also tells us we can also get a lower bound from the theorem. So theorem Nash-Williams inequality. In this theorem, we first introduce one notion. It's called an edge cat-set. So suppose pi is an edge cat-set. It means that this pi is a subset of edges, and it satisfies the following property. So for any path from A to Z, it must include some edge in this pi. Or in other words, it means that if we cut all edges in this pi, then there's no path from A to Z. So this is why we call this as an edge cut set. So if we cut all edges in pi, then there's no path from A to Z, and the graph becomes disconnected. So for example, suppose this is our network, and this is A, and here is Z. And if we cut these two edges, then A is disconnected from Z. So the set of these two edges is an edge cat-set. Or there are also other edge cat-sets. Suppose we cut these four edges, then A is also disconnected. So this is another set of edge cat-sets. So this is the notion for edge cat-set. And Nash-Williams inequality says if pi k is a disjoint union of edge cut sets, so they are disjoint edge cut set, then we can give a lower bound for the effective resistance. So this is a lower bound for the effective resistance. The C is just a conductance on the edges. Okay, so to prove this theorem, we know that it is sufficient to prove to show that for any unit flow theta, the energy is bounded below by the right-hand side. Because we know that this guy is the inflow of all possible energies of a unit flow. So if for anyone it is bounded from below from this right-hand side, then the inflow is also bounded from below by the right-hand side. So it is sufficient to show that for any unit flow theta, the energy is bounded by this right-hand side. So now what is the relation between this right-hand side and the energy of flow? So for any cut set, for any edge cut set pi, what we know is if we cut all edges in this set, then the flow can't go from A to Z. So this tells us the flow along all these edges has to be greater than 1 because we just stop all the flows going from A to Z, and we know that the total amount should be 1. Okay, so this is a special property for this edge cut set. Okay, and for the energy of flow, we know that the energy of a flow has this expression. So it looks like it has the same expression in this way. Okay, by Cauchy-Schwarz inequality, we know that this guy times this guy is always greater than 1. So now we move this quantity to the right-hand side. What we know is so if we just calculate the energy of flow in this for the edges in this edge cut set, we always have that this part has a lower bound. So this is true for any edge cut set. And now for the energy of the theta, we know that it is this quantity summing over all possible edges. And since this pi k is disjoint, we know that if we just take all edges in the union of pi k, then this is a subset of the edges. And by the relation here, we have that okay, so this is the Nash-Williams inequality. So now just a quick summary. We have introduced the energy of flow, and we show that the effective resistance is the minimum of energy of unit flows. And we also prove this Nash-Williams inequality. The Nash-Williams inequality gives us the lower bound of the effective resistance. So generally, if we want to estimate the effective resistance from the theorem above, we know that lower bound. To find that lower bound, we can use Nash-Williams inequality. And for the upper bound, we know that this guy is bounded from above by energy of any unit flow. So we just need to construct a good So we just need to construct a good unit flow so that the energy is not big, so the energy as small as possible. Then for any such unit flow, it gives an upper bound on the effective resistance. So by the theorem in the first lecture, we see that in order to estimate effective resistance, lower bound, we can just use Nash-Williams inequality. And for the upper bound, we can just construct a good unit flow. Okay, next. Let us see a precise example how to estimate the effective resistance. In this example, so our network is the rectangle n by n square. And our source, A, is the upper left corner. So the coordinate is 1, 1. And our sink is the right upper corner. The coordinate is n, n. So this is an n by n box. And in this exercise, we want to estimate what is the effective resistance of this network from A to Z. So along the diagonal lines. And the conclusion says, in fact, as n goes to infinity, this effective resistance will increase as log n. So there is a lower bound is 1/2 of log n, and the upper bound is 2 times log n. So as n goes to infinity, it will increase more or less the same as log n. Okay. So first, lower bound. So for lower bound, we want to use this Nash-Williams inequality. So then we need to find a collection of disjoint edge cassette. And here we see that the set of these two edges is an edge cassette. So these two put together is an edge cassette. And then these four put together is also an edge cassette. And they are disjoint. So in this way, we can define a sequence of edge cassettes. So we call them pi 1, pi 2, to pi n. And they are a disjoint collection of edge cassettes. And by Nash-Williams inequality, we know that the effective resistance is greater than k from 1 to n. So this is Nash-Williams inequality. And now we assume our network has unique resistance on every edge. So this C is always 1. And in this summation here, we're just counting how many edges we have in pi k. And the number of edges in pi k is 2k. So here we see that this is 1/2. One over k. And this is greater than 1/2 log n minus 1. Okay, so lower bound by Nash-Williams inequality. And for the upper bound, so we want to construct a nice unit flow so that the energy is small. So what is a good strategy to construct this unit flow? So one possible construction is so we can set all edges here to have flow 1, and all other edges are 0. Then this is a unit flow. But the energy of this unit flow is very big. So it's, the energy of this guy has the same order as n. So this is not a good upper bound. So this is not a good unit flow. So what is the strategy to construct a good unit flow? So the idea would be we want this unit flow to be symmetric in any possible way. So the more symmetric, the more better. So suppose this CK is the collection of edges that has distance k from the origin. So CK is almost a circle with radius r, circle with radius k. So the CK contains all edges that has distance k from the source A. And our idea is we hope that for any E in CK, the flow on this edge is almost the same as 1 over k. So because we know that the number of edges in CK increases k, and we hope all these edges to spread symmetrically. So we hope that each flow, for the flow on each edge is almost the same as 1 over the number of CK. So it will look like 1 over k. If we can succeed to find such a unit flow, then let us check what's the energy of this flow. Okay, so this is the energy of this flow. And for E in the circle CK, we know that we hope this theta k is 1 over k. So theta square is 1 over k square. And this effective, and this resistance is unit resistance. So this is the, so this will be the same order of our energy of this theta. And then we know that the number of edges in CK increases k. So this is almost the same as 1 over k. And this summation will increase like log n. So this is how we construct the upper bound. So we construct a unit flow. We hope that this unit flow can be symmetric as symmetric as possible. And then this means that we hope along every circle, the the flow has just the uniform distributed along this circle. And for such a unit flow, we see that the energy increases log n. So this will give the upper bound. So for this precise construction, so there is a precise construction to construct a unit flow satisfies the relation I mentioned here, and it will be discussed in today's recitation. Okay, so this is this example. And then we have 5 minutes break, so we resume at 10, and we continue with countable state space Markov chain. So before we start the next lecture, everything we covered up to now is for finite state space. So we introduced the ever notion for Markov chain, and we show that there's stationary distribution and there's convergence theorem. And for all of them, and we also have an estimate for the convergence rate to the stationary distribution. We show that it will converge exponentially fast, but everything there depends on the fact that our state space is finite. And today we will continue with countable state space. So now they are not finite, but they're still countable. So first, let us check what kind of notion can be generalized from finite to countable state space. So first, this is the definition of Markov chain. Then it is exactly the same as the finite state space. So omega now is countable. And the P is the transition matrix. And the Markov chain is a sequence of random variables satisfies the following property. So this property tells us, given what happens after time n, the conditional probability to jumping from x to y is always the same. It's given by pxy. So it is independent of what happens before time n. It only happens what is the last step, and then the jumping probability is always given by this transition matrix. So this is exactly the same as the finite state space case. And the only difference now here is, when it is finite state space, our transition matrix, suppose the size of the state space is n, then the transition matrix is n by n matrix. But now, if our state space become infinite, now this P is no longer a finite matrix, so it is an infinite matrix. So there are infinitely many columns and infinitely many rows. So this is the only difference, but the definition is exactly the same as in the finite state space case. Okay, so this is definition, and then let us check stationary distribution. So stationary distribution is also defined in the same way as before. So if pi is a stationary distribution, it means that this is a probability measure, and pi times p equals pi. So this is also defined in exactly the same way as before. Okay, and irreducible. So irreducible when the state space is finite, it means that for any state x and y, there is a strictly positive chance to jump from one state to another state. And now in the countable state space, it is still defined in the same way as before. But now, an important difference between for the infinite state spaces, when the state space is finite, we have proved that if the Markov chain is irreducible, then there exists a unique stationary distribution. But now, this proof doesn't work for the countable state space, because in that proof, we use the fact that the state space is finite. Okay, so irreducible stationary distribution is defined in the same way as before. But at this step, in fact, we don't know whether there exists or there is a unique stationary measure now, because the proof for the finite doesn't work for the infinite case. Okay, and then the heating time and first return time is defined in the same way as before. So this is the first, this is the heating time. So it's the first time that hits a vertex X. And this is the first return time. It means that if n starts from 0, so if we start from X, then this is the first time that we go back to X. So this is different for this is different from the heating time, only when our Markov chain starts from X. Okay, the first important notion for infinite state spaces, there is one notion that there's no such property in finite state space, but for the infinite state space, the property is called a state can be recurrent or not. So a state is recurrent if the probability that the first return time is always finite is 1. So if you still remember what we proved in the first lecture we showed that for finite state space, this is always true. But now, our state space become infinite, so this is not always true then. So when this is still true, we call the state is recurrent. And when it is not true, we call the state is transient. So this is the first difference between finite state space and the infinite state space. So just a remark. So when the state space is finite, every vertex is recurrent. We have proved this. But now, when the state space becomes infinite, there are two different kinds of scenarios, so recurrent or transient. Okay, so this is the first difference. And then, a lemma tells us if one of the states is recurrent, then all the states are recurrent. So this lemma says, suppose our transition matrix P is irreducible. Then the following two statements are equivalent. First, one of the states is recurrent. Second, for all the states, they're recurrent. So before we prove this lemma, we can say that if a Markov chain is irreducible, and if one of the states is recurrent, we can show that all the states are recurrent. So then this recurrent or transience is a nature for the Markov chain, not for just one vertex. So after we prove this lemma, we in fact classify irreducible Markov chain into two categories. One category is recurrent everywhere, and another category is transient everywhere. Okay, proof. So if one vertex is recurrent, then all vertices are recurrent. So suppose some vertex is recurrent. And we want to show that for any x and y, we always have tau y plus is finite. And there are 3 steps. So first, we change x0 by some other vertex. So first, we show that this probability always equal 1. So here we just replace this x0 by some other vertex y. And second, we show that we replace this x0 by some other vertex. And then finally, we replace both of them by some other vertex. So this is the 3 steps of the proof. So we start from the fact that this equality holds for some x0. First, we replace here, and then we replace here, and finally, we replace both of them. Okay, so first, why the probability that tau y is finite is 1. So we want to calculate the probability that tau y is finite. And the only quantity we know is tau x0 plus is finite. So now we compare this tau y with tau x0 plus. So it can either happen before tau x0 plus or happen after tau x0 plus. So we just compare which happened before, we just compare tau y and tau x0 plus and see which happens earlier. Okay, so suppose we denote this probability as Q. So we want to show that Q equals 1. And then let us check what's the probability here. So the probability here says we start from x0. And we visit y before we're going back to x0. And we denote this probability as p. And by irreducibility, we know that p is always positive. Because we know that the probability to jumping from x0 to y and then to x0 for some fixed path, it has positive probability. So of course, this guy is always positive. And then let us check what happens to the second quantity here. So the second quantity says it returns to x0 before hit y. So the first part is it is 1 minus p because it hits y after tau x0 plus. And after it's going back to x0, we know that this is just a new Markov chain starting from x0. And now we are just calculating what's the probability that tau y is finite. So the second part of the probability is exactly the same as Q. So now let us rewrite this expression. What we have is Q equals P plus 1 minus P times Q. And we simplify this equation. It tells us P times 1 minus Q equals 0. And here, since P is strictly positive, we know that Q has to equals 1. So this shows that the probability for tau y is finite is 1. Okay, so this is the first step. For the second step, so we want to find out what's the probability that also when x and x0 are distinct, then there's the heating time is the same as the first return time. So there's no need to put this plus sign there. Okay, so if we start from x, what is the heating probability for tau x0 to be finite? And again, the only property we know is this one. So we want to start from here to find the probability this. Okay, so let us check what's the probability for this event. So first of all, this event says we start from x0, we first hit x and then going back to x0. By irreducibility, we know that this probability is always strictly positive. And then by Markov property, what we have here is so if we stop at the time that we hit x, what we know is we start from x0, we hit x before hitting x0. So this is some probability. This has the same probability as p. And after we hit x, we know that this is a new Markov chain starting from x. So the second part of the probability is px tau x0 is finite. And since p is strictly positive, we know that the probability for this event has to be 1. Okay, so this is the second step. The third step, we replace both the starting point and this point by some by some other vertex in the state space. So we want to calculate the probability that we start from x and we hit y in some finite time. So of course, this probability is greater than we first hit x0, and after we hit x0, we hit y in some finite time. So this is greater than this one. So this notation means after we hit x0, the first time that we hit y. So of course, this event implies that we hit y in some finite time. And for this event, let us check. So the first part of the probability is it starts from x, hit x0 in some finite time. And after we hit x0, we know that this is a new Markov chain starting from x0. And now we want to calculate the probability that it hit y at some finite time. And by the first and second step, we know that these two probabilities, both of them are 1. So the product is also 1. Okay, so this lemma tells us if we have an irreducible chain, then one of the states is recurrent implies all states are recurrent. So this tells us there are two possibilities for irreducible Markov chain. Either all states are recurrent or all states are transient. So this classifies the Markov chain into two categories. And at the end of today's lecture, we will show that for simple random walk on Z2, it is recurrent. And for simple random walk on Z3, it is transient. Okay, so this is the recurrence and the transience. And next, let us check what kind of notion that for the network can be generalized to the infinite state space case. Okay, so let us check how notion can be generalized from state network to finite, from finite network to infinite network. So now suppose G is an infinite connected graph, and which with edge conductances. So this is definition of an infinite network. And now let's check how to generalize the definition for effective resistance. Because for the finite state space, we fix two vertex A and Z, and we say that this is the effective resistance from A to Z by voltage and the flow and everything there. But now, our network become infinite. And how to generalize, how to define this effective resistance on this infinite network? So the idea is, we want to approximate this infinite network by finite network and show that every quantity we are interested in is just the limit of the finite case. Okay, so approximate infinite network by finite ones. So here is just some precise definition of how we construct the finite approximation. So suppose G is the infinite network. And now first we define a finite graph Gn. So it's just a finite graph. Vn is a finite subset of V. And En, of course, it is also a subset of E. But En and Vn are chosen that if there is an edge, if the two vertices of an edge are in En, then the edges between them is also in V. So this Vn and En are chosen in the way that if two vertices are in Vn, and if there is an edge in the infinite network, then it is also contained in this finite network. So this is in the common way. So this has the same. This should be the idea. Okay, so in fact, this Gn, you can just will it as a cutoff of the infinite network. So suppose we have Z2. This is an infinite network. And now we just cut off this network by the finite one. So this is Gn. So we can choose this Gn to be the n by n box. And as n goes to infinity, we see that the sequence of Gn will approximate the infinite network. But when we generalized all the notion of the effective resistance and the flow and everything there, we find that there is an important difference between this Gn and the infinite network. Because in this Gn, we don't have a source, we don't have a sink. If we just cut it out, then can you tell me where is the sink? Because in the infinite network, suppose we are in Z2, if we choose this is the source, then we put a flow, then the flow will spread out all the way to infinity. But if we just cut this graph by an n by n box, then we don't know where is the source, where is the sink. So we need to define a modified Gn star. So it's almost the same as Gn. So the only difference is we add one sink. We add one sink on top of this cut. So Gn star is we put one edge, one vertex, Zn. It has the same role as the sink in the finite state space. And after we add this vertex, how it is connected to the finite edge. So the idea is, if there is an edge here from our cutoff to the outside, then we put an edge to the sink. Okay, I shouldn't draw 4x4, I should draw a 3x3 box. So this is our Gn star. Suppose Gn is the cutoff. And Gn star is just on top of the cutoff. We put one vertex Zn, and it has the same row as the sink. And then for any vertex inside this Gn, if there is an edge from here to outside, then we put an edge from here to Zn. And the conductance on this edge is the same as the conductance for this edge that's connecting to outside. So this is Gn is the cutoff. Gn star is a modified graph of Gn. So the only difference is we put as a sink. And now we can generalize all the notations we want. So first, effective resistance. So the effective resistance from the source to infinite would just be the limit of the effective resistance in the finite graph case. Of course, before we say anything about this effective resistance, we have to show that this effective resistance doesn't depend on the choice of this cutoff. So I won't prove the detail, so it is well defined. So it doesn't depend on the choice of the sequence. So this is the first generalization of effective resistance. And next, whether the property for finite case also holds in the infinite case. The first property is the relation between effective resistance and escape probability. So this is what happens in the finite state space case. So this is the escape probability. This is the effective resistance in the finite state space case. And now, our effective resistance is just the limit as n goes to infinity. And then to the left-hand side here, it is the escape probability. So this tells us we start from the source. We hit Zn before going back to A. And as n goes to infinity, because this Zn goes to infinity, it means that we never come back to A. So this is the property that this is what happens in the finite state space case, and this theorem tells us it is also true in the infinite case. And here, a first corollary is we see that the left-hand side is closely related to recurrence and transient. So if the left-hand side is positive, strictly positive, then this Markov chain is recurrent. And the left-hand side is strictly positive means this effective resistance is finite. So this guy is finite if and only if the Markov chain is transient. So the effective resistance is finite if and only if the Markov chain is transient. Okay, so this is the first property. The second property we want to generalize is the relation between effective resistance and energy of a flow. So what about the energy of a flow? So first, for any flow, we generalize the definition for flow. Theta is a flow. It is almost defined in the same way as before. So it means that at the source, we only have flow out. And at all other vertex, flow in equals flow out. And now since our sink is infinity, so there's no sink, there's no restriction to say that the sink has only flow in because it is infinite. So this is exactly the same definition as in the finite state space case. And then we can define the energy in exactly the same way. So flow and the energy of a flow. So they are defined in exactly the same way as the finite state space. And in the finite state space, we know that the effective resistance is the inf of the energy of unit flow. And this theorem tells us, in the infinite case, this is still true. Okay, so why it is still true? So first, recall what the proof for the finite case. In the first step, we show that the inf will always be obtained. And there we use that because this E theta is a compact subset of some compact set. So the minimizer is always, the inf is always obtained. But now since our state space become infinite, the first step doesn't work. So we can't repeat exactly the same proof as in the finite state space case, but we can use approximation. Okay, so first we show that for any unit flow, the effective resistance is less than the energy of this unit flow. So why this is true? For any unit flow, let theta n be the restriction of theta to the finite approximation. Then we know that since the energy of the theta n it is a summation over all edges E, but just in Gn star, so that the number of the edges is less than the edges in G. So we know that this summation is always is lower than the energy of theta, because this is just a cutoff. We just stop this infinite summation up to some finite time. And for the finite case, we know that for any unit flow theta n, this is greater than the effective resistance from A to Zn. So from this guy is less than this guy, this is the property from finite case. And this guy is always smaller than this guy because we're just taking summation over some part of the edges. Okay, so now the effective resistance from A to Zn is less than energy of theta. Let n goes to infinity. We have that the effective resistance from A to infinity is bounded by the energy of flow. Okay, so this shows one side of the theorem. So it says that effective resistance is less than the inf. And for the another part of the proof, we also need to show that the effective resistance is the inf. Okay, so to the another side, we need to study what happens to the current flow. So let I be the current flow. And In is the restriction to the finite approximation. So first, in the finite case, we know that the effective resistance is the energy of In. So this is the property from finite case. And now we know that the left-hand side will converge to converge to the effective resistance from A to infinity. And the right-hand side, because the right-hand side we're just calculating the energy of the edges in Gn star. As n goes to infinity, since Gn star exhausts all the edges of Gn. So the right-hand side just increase to the energy of current flow. So combining these two, we say that this effective resistance is still the energy of the unit current flow. Okay, so this theorem tells us the relation between effective resistance and energy of flow is still true in the infinite case. And then what about Nash-Williams inequality? So this is Nash-Williams inequality if you just change it to the finite version. So now this is just a change this sink to infinity. And now for the proof of Nash-Williams inequality, you can just repeat exactly the same proof. There's nothing difference between the finite and the infinite case. You can just repeat exactly the same proof, and this will show the lower bound. So this Nash-Williams inequality is also true for the infinite case. Okay, so now for the countable state space. First, we introduce what's the notion for recurrent and the transient. So they are characterized by the escape probability. So when it is recurrent, this escape probability is 0. And when it is transient, this escape probability is strictly positive. So for countable state space chain, they are recurrent, and the recurrence and the transience is 2 cases. And then we generalized all the notions we know from the finite network to infinite network. So now, in fact, what we have done is we have some criteria to check a Markov chain is recurrent or transient. So this theorem says the following 3 statements are equivalent. First, the Markov chain is transient if and only if the effective resistance is finite. This is because the relation here. So this guy has strictly positive probability if and only if the effective resistance is finite. And because of the relation between effective resistance and the energy of flow, it is also equivalent to say that there exists a flow or a unit flow that has finite energy. So the equivalence between 2 and 3 is because of the relation between effective resistance and energy of flow. So now we have, if we have a random walk on the network, we want to decide whether it is recurrent or transient. We can either check whether the effective resistance is finite, or there exists some flow that with finite energy. And since Nash-Williams inequality only gives us the lower bound for the effective resistance, so this only gives us a criteria to check whether it is recurrent. So by Nash-Williams inequality, it says that if we can find, if there exists a collection of disjoint edge-cat sets, such that this expression is infinite. And then, because we know that this expression gives a lower bound for effective resistance, so it diverge implies the effective resistance diverge. The effective resistance diverge means we are in the scenario of a recurrent. Okay, now we can use all these tools to check a Markov chain is recurrent or transient. So now we can prove this property. So for simple random walk on ZD, it is recurrent when D is less than 2, and it is transient when D is greater than 3. So first, observe that if we can prove simple random walk on Z square is recurrent, so for when dimension equals 2, if it is recurrent, we know that if one of the coordinate of it is just a simple random walk on Z1, so of course Z1 is also recurrent. And this is also true for simple random walk on Z3. So if we show that on Z3 it is transient, of course in higher dimension it's also transient, because in higher dimension the first 3 coordinates is just simple random walk on Z3. And if we know that the first 3 coordinates can't come back to the origin, of course the whole walk can't go back to the origin. So here we only need to show that it is sufficient to show that simple random walk on Z2 is recurrent. And this implies the simple random walk on Z1 is recurrent. And we only need to show that the simple random walk on Z3 is transient, because this implies that for higher dimensions it's also transient. Okay, so proof. So first for Z2, why it is recurrent. In order to check it is recurrent or transient, we have several tools. So Nash-Williams inequality will give us whether or not it is recurrent. So this gives us a criteria for recurrent, but this is not even only if. So this is just tell us if we can find such a collection of disjoint edge cassette, then it is recurrent. Or we can check what's the effective resistance of this network Z2. Okay, so for Z2, we are lucky because it is easy to find a disjoint collection of an edge cassette. Okay, so suppose this is the origin. And we see that these 4 edges is an edge cassette. And this edges is also an edge cassette. So this is pi 1, this is pi 2, and we can define in a similar way pi 3, and so it's, roughly speaking, it is on the Z square, and it's just a circle. And we can see that this collection of edge cassette is a disjoint collection of edge cassette. So this pi n, this pi k is disjoint edge cassette. And for each pi k, so now we can check what's the quantity here, whether it's divergent or finite. So what is this quantity? So now, because we are the simple random walk, so in fact it is assumed that this is equivalent to say that all conductance are units. So now we are just counting how many edges are there in pi k. So how many of them? So in fact it is more or less the same as 4k. So the number of edges in pi k is 4k. So then this quantity is just 1/4 summation for k from 1 to infinity of 1 over k. And we know that it diverges. So since this quantity is divergent, we know that simple random walk on Z2 is recurrent. So Z2, recurrent. Okay, so now let us check for Z3. So it is transient. Transient is equivalent to say that there is some unit flow that with finite energy. So the idea is we can construct a nice unit flow with finite energy. So now what's the idea of this construction? It's the same as before. So we want this flow is symmetric and is as more symmetric as possible. So what is if this Sk is the sphere of radius k, then we know that the number of edges in Sk is more or less the k squared. So it's a constant times k squared. And now what we do is we construct this unit flow theta e equals 1 over k squared for E in Sk. So we hope around the sphere of radius k, all the flows are uniformly distributed. So this is the idea of the construction of the unit flow. So suppose we can construct such a unit flow. Then let us check what's the energy of this unit flow. So this is the energy of this unit flow. And now our resistance is a unit, so it is 1 everywhere. And this theta e is 1 over k squared. So theta squared is 1 over k to the power 4. And now summing over E in Sk. So this is just counting the number of edges in Sk. And the number of edges in Sk is k squared. So what we have is the energy will increase as the summation of 1 over k squared, and it is finite. So since we can construct a unit flow with finite energy, then this implies that this simple random walk has to be transient. So this shows that a simple random walk on Z3 is transient. And you will also see other proofs for the simple random walk is transient or recurrence in the next recitation. Okay, I will stop my lecture here. And also, so if when this recitation sheet, the exercise sheet is available, I will put it online. Okay, so when the exercise sheet is available, I will put it online. So today's exercise sheet is already online last week, and I also the sheet for the next week is also available here. You can check because in the next lecture, so the lecture on 19th, so there will only be 1 hour of the lecture and 2 hours of the recitation. So it is better that you read the exercise in the exercise sheet before you come to the recitation. Okay, so I will stop here.